السلام عليكم ورحمة الله. اليوم إن شاء الله استكمالا لدورة اللي هي Introduction to Chemical Engineering Diagrams. بالمحاضرات السابقة رح نعمل ريفيجن. درسنا البلوك فلو دايجرام ودرسنا البروسيس فلو دايجرام، واليوم إن شاء الله رح يصير تركيز، رح نعمل ريفيجن بسيط على two type of diagrams, the block flow diagram والprocess flow diagram. In details, we will study the piping and instrumentation diagram. The next is the last lecture. We studied what is chemical plant and why we need them. And as you remember, we told that the science starts with experiment in lab scale. يعني احنا بنبدا عمليه التصنيع دائما في اللاب سكيل، وبعد ما نخلص اللاب سكيل ببدا عمليه تكبير to enlarge the scale of production. We move towards chemical plants. As you remember, the lab scale should be maximized or scale up to a full detailed, very large plant. Okay. In the last session of this training course, we talking about types of chemical diagrams. We have three main common types, if you remember: block flow diagram, process flow diagram, and the major of this session is piping and instrumentation diagram. And we talk that there is other types of diagrams in chemical engineering: concept diagrams, plant layout diagrams, and 3D diagrams. In the block flow diagram, we told that we shows overall processing picture of a chemical complex, and flow of raw materials and the products may be included in the BFD. يعني بنقدر احنا نشوف كيف تدخل عندنا المواد وكيف بتطلع. In the block flow diagram is a superficial view of facility. Chemical information is missing. The block flow diagram just for showing the idea. احنا بس بنوريكم الفكرة حوالين البلوك flow diagram. وبرضه حكينا إنه there is 7 things should be provided in the block flow diagram: operation, major flow lines as arrows. We shown them with arrows giving direction of a flow. The flow goes from left to right. You have to make your diagram from left to right. Light stream, the gases towards top, and the heavy stream, liquid and solid, towards bottom. So هون احنا we have to draw the block flow diagram considering the light and heavy streams. Critical information unique to process supply, such as conversion, such as molar flow rate, maybe such as the components in each stream. برضو كمان number 6, if lines cross, then the horizontal line is continuous and the vertical line is broken. This is very important note. If you have to cross 2 streams together, make the horizontal line continuous and vertical line broken. Simplified material balance provided. The block flow diagrams aims to make material balance, or we use the block flow diagram basically to accomplish the material balances. There is another type, or the second type, the more developed type, is the process flow diagram. In the process flow diagram, we represent a quantum step up from the BFD in terms of the amount of information that it contains. There's many items should be shown in the BFD diagram, such as major equipment, principal flow route and main control involved from raw materials feed to final products. This is not for control loops. It should not be in the process flow diagram. But we have a piping and instrumentation diagram, and we can show everything regarding the control and instrumentation in this diagram. Key temperature and pressure corresponding to anticipated normal operation. You have to put the temperature and the pressure for most streams, especially the main streams. Material flow rate and composition also should be shown in the process flow diagram. And design duties and sizes of major equipment as a table. We can show the material flow rate and design duty basically in the tables, okay? At the end of the process flow diagram. You don't have to put everything in the diagram. You can add some tables to discuss everything, okay? This table we took it in the last class. How we can make name or put name for each equipment. For example, we use C for compressor or turbine, E for heat exchanger, H for fired heater, P for pump. This is not, you don't have to use only these samples. You can make your own sample based on your university standards or your company standards, etc. Okay, here if you see, this is old-fashioned. This slide is old-fashioned for recognize the stream ID, temperature, pressure, liquid flow rate, gas flow rate, molar flow rate, and mass flow rate. This is the flag should be used if you want in your process flow diagram to show all of these process variables. Okay, and this table give me the required information for process flow diagram. You have to give all of these. And optional, you can make one or more than one of these variables. For utility streams, there is a specific samples for each utility type. For example, we have LPS, low pressure steam, medium pressure steam, high pressure steam, and if you refer to last lecture, you can know how and why we use each of these utility streams. Okay, going to the major title in this class, which is the piping and instrumentation diagram. What is the piping and instrumentation diagram? First of all, we have to show and give the reason why we need a piping and instrumentation diagram. Why it is not enough for chemical engineer to read the block flow diagram and the process flow diagram. First of all, the controller is needed. The controller is needed to keep the process under steady state conditions when the process has some disturbance. For example, if we have high temperature in a reactor or any other distillation column, any other unit operation, the controller try to return the normal operation by making some actions to keep the unit operation at design operation conditions. The main variables that should be controlled are, we have some variables, main variables or very common variables to be controlled, such as temperature, pressure, level, as well as flow rate. If you don't have liquid in your unit operation, so you don't have to include level control loop for in your piping and instrumentation diagram. The third thing process control instrumentation improves the quality of the product, and there is opportunity for additional business for control. We can make, for example, we can control a new product quality or new operation conditions if you have any modifications in your unit operation or plants. Here we want to know how we can control. First of anything, we have to measure the performance, measure the control variables. Then this measurement goes to controller. In the controller, we will make a comparison between the set point and the measured variable. If there is equality or the measured variables is within the range of acceptable operation, so the control will do nothing. But if we have a higher or lower than the acceptable range of control variables, we have to take an action. What the type of this action? It depends on the control philosophy. Okay, what is the piping and instrumentation diagram? Here we want to define the piping and instrumentation diagram. The piping and instrumentation diagram, P and ID, also in some references maybe called mechanical flow diagram, MFD. The most common is B and ID. In some plant or countries called this diagram LED, line engineering diagram. Okay, and this diagram provides information needed by engineers to begin planning for the construction of the plant. The piping and instrumentation diagram, okay, include the control loop, the valves, the spare equipment. For example, if we have a backup pump, maybe we have many valves to back up the control valve, and etc. The piping and instrumentation diagram does not include the followings: the operating condition. You don't have to include the temperature and the pressure, for example, in the piping and instrumentation diagram. Why? Because we have a process flow diagram aims to show these conditions. The stream flow rate, no way to include stream flow rate. Equipment location, we cannot make the location or indicate the location of the equipment. Pipe routing, for example, pipe length and pipe fittings, pipe size, etc. The support, structure, and foundation. Okay, the basics information should be included in the piping and instrumentation diagram, as I told before. The spare unit, parallel units, summary, details of each unit. For piping, the size, the schedule, material of construction, the insulation. For instrument, the indicator, recorder, controller, show instrument lines. For utility, we will identify the entrance of the utility, the exit of the utility, exit to waste treatment facility. All of these information should be included in your piping and instrumentation diagram to be within acceptable standards. Here I have from a book, I give you an example of piping and instrumentation diagram for a distillation column. And as you can see, there is many flags and many symbols in this diagram. To know and to read this diagram, and later on you can draw a piping and instrumentation diagram, you have to know each symbol, what the meaning of each symbol. Okay. First of all, we have three circles, three types of circles. The circle with vacant, there is no line inside. This is indicate that an instrument located in the plant. Okay, but if we have a continuous line inside the circle, the instrument located on the front of panel in control room. And if we have the dashed line inside the circle, the flag, an instrument located on back of panel in control room. And for the connection, the lines, the capillary is continuous line, pneumatic has two dash line, as you can see, the pneumatic, the electrical. What the difference? The capillary is used for measured the control variable. There is a measuring. This line show that we have a measure of anything, any parameter. The pneumatic, it is an air signal. It is an air signal by compressor or compressed air to open and close the control valve, the diaphragm. The electrical, it is the signal transfer from control to from a flag or an instrument to another inside the control room. And we can see the example later. For example, here, regarding the letters inside each flag, the first letter A, B, C, D, E, F, H, I, J, K, L, M, O, P, Q, R, S, T, V, W, Y, and Z. For example, if you see A as a first letter inside the flag, you will know that A is referred to analysis. There is an analysis of the data in this flag or in this instrument. P is burner flame. C, conductivity. The most important parameter is P is referred to pressure, F, flow rate, T is temperature, L is level, and as we discussed before, we have four main control variables should be analyzed in the control loop, which is flow rate, level, pressure, and temperature. Okay. The second or third letter, the maximum number of letters inside the flag should be 3. Yani maybe you will deal with 2 letters inside the circle, okay, or or 3 letters. For example, if we have TI, T is the first letter. T is the first letter. Temperature, right? Indicate temperature. I, we go to I, second letter, indicate. So we have temperature indicator. It's a gauge showing the temperature, maybe on the plant, on the front, on the front of panel in control room or back of panel in control room. This depends on the lines here, the continuous line, the vacant circle or dashed line circle. Okay, I think this is very clear, and I will give many examples to show how we can draw the control for each process variable. For example, let's go to controllers for flow control loop. For example, here, this a flow meter. This is a flow meter. From a flow meter goes to FE. In the FE, if we refer to this table, F is indicate flow rate, E is element. So this is a flow rate element. What the objective of this element is to measure the flow rate. Then, as you can see, this is a continuous line. So this is capillary line. This is a capillary line. This signal goes to FT. FT is flow rate transmit or transmitter. This transmitter converts the signal from capillary signal to electrical signal. Why? Because the controller cannot read the capillary signal, but it can read electrical signal. Then, as you can see, we have two alarms, flow alarm low and the flow alarm high. If the flow rate is very high, so there is an alarm located in the front panel of the control room, gives alarm for control engineer or control operator that there is very high flow rate goes to the equipment. Okay, and the same if there is low. How I can read this these letters? We will go to this table: flow rate, A alarm, the second letter, and H is high. And if it is L, so this is L, low, light or low. Okay, good. Okay, then we goes to FRC. This is flow or flow rate record control. This is the controller. The conversion occurred inside this device. After that, the electrical signal, the decision electrical signal goes to FY. What FY? It is a flow relay. What the objective of this flag is to convert the electrical signal into pneumatic signal. And finally, we have this control valve, which is closed and open partially to increase or decrease the flow rate to the or to the unit. Here we have 3-inch schedule 40 carbon steel. CS is referred to carbon steel. This is the size of this pipeline. Here also I will discuss later, but for now, this is a control valve. We have two isolated manual gate valve, and we have manual control globe valve. I will discuss everything about this arrangement later on in this class. Here we have a temperature control. Here, the focus is in this section. As you can see, there is a temperature element. The signal goes to temperature transmitter. Electrical signal goes to indicate high or low alarm, temperature alarm high and temperature alarm low, goes to TRC, temperature record control, and then the signal goes to TY, which is the temperature relay, and finally by pneumatic signal we can control the heating. Maybe here we have a heat exchanger. This is a reboiler, so maybe we have a steam, low pressure steam, medium pressure steam, or high pressure steam. This symbol gives the insulation. This means this line is insulated. Why? Because we have what? Here we have a steam, so the pipeline should be insulated. Okay. Going to pressure control loop, the same structure, BE, pressure element, pressure transmitter, a pressure alarm low and high, a pressure record control, and pressure relay goes to the double bleed arrangement or the control valve arrangement. And for the level, the same, you can check that we have the same structure of all control. So this is full HD image, and you can note that we have 3, 4, 6, 7, maybe 1. Okay, all of these. This is a utility connection. As we discussed before, we have to discuss anything about the utility, and we have all of these. Okay. Now I want to make tip or the full discussion for this arrangement. First of all, we have a control valve. We depend on this valve basically to control the control variables, for example, flow rate, temperature, etc. If this control valve has a failure, for example, so what we can do as engineer, before this arrangement, or if we don't have this arrangement, we will make shutdown. We will have emergency and disturbance in our unit operation. So how I can take benefit of this arrangement? If the control valve has any issue, so I have to close the gate valve A and C. Then, using the glove valve, the flow rate cannot go to this line anymore. And we can, using the glove valve, to what? To regulate and control the plant manually. How come manually? In the control room, the control engineer can change or can increase or decrease the flow rate or cooling flow rate or anything. So we have here the end of second period or second class for engineering drawings in chemical engineering. And we will have a break. Then we can give an example as a case study to make a control piping and instrumentation diagram for a reactor. See you later and thank you. Again, everybody, hello. It's Engineer Khaldoun Al-Ashi. We will continue this lecture about the piping and instrumentation diagram. And I will give you an exercise. We will make an exercise with each other about the case study. So the case study is solved in this presentation, this video. So I will go to a screen, another screen. It's a manual screen, a touch screen, and I will make with each of you the exercise, or I will solve the piping and instrumentation diagram for a reactor. Okay. Here we have a fluidized bed reactor or a fixed bed reactor. Okay. First of thing, we have to know how many variables or how many control system or how many controller I should include in my unit operation to make a full control, automatically control for this unit operation. This can be done by accounting for degree of freedom. The degree of freedom, it's very simple and can be done by, if we have the degree of freedom, the degree of freedom is the number of unknowns minus number of equations, okay, give me the degree of freedom. For example, here in this reactor, we have 17 variables. The 17 variables, for example, the temperature of line 139, the temperature 140 and so on for from 139 to 147. The pressure of these lines, the flow rate of this line, in addition to the flow rate of coolant and the temperature of coolant. This reactor using cooling water to keep the temperature at 70 Celsius of operation. Okay, the energy balance, the number of equation or relations, the energy balance on the reactor, C balance, H balance, N balance, the mass balance, atomic balance for each component, the energy balance on the jacket, okay, the energy balance of the jacket, the cooling jacket, and we have 6 defined variables, which is the inlet and outlet temperature, in addition to the conversion. If you count, we have 17 variables, 6 relation, and 6 defined variables. So the number of degree or the degree of freedom is 17 minus 6 equal to 5. And here you can check all of these slides, okay, in the video, and you can see that we can, using Visio, we can make a full piping and instrumentation diagram for the this control or this reactor, and we can if we have some space in the drawing, we can make this table to show what the meaning of each element. Okay, I will go now for manual screenshot to make a practice with each other and make full discussion and give these tips of each control element in our plant, in our example. Okay, let me change to so touch. Okay. Now okay, 1 minute. Now, first, we will discuss the flow control. I will draw a control loop like this. We can also use Visio to discuss or to draw this control loop. Okay. This array like this or like this. Next one is a capital line. Here we have a orifice. Then the flow goes to flow transmitter, from transmitter. control goes to F relay and by negative signal. For this line, I have to make it rationalize. Now I will make full discussion to give the steps of control. First of all, flow rate. FE measure. And then maybe we have gas. Flow rate. System test. As we discussed in the presentation, it's used to convert measurable readings as we discussed later. Three, point analyzer, flow rate analyzer, and controller. Oh, is all right. So, so flow rate along flow around one, which is what L. What is this? Okay, just to find step, we have a low alarm, and we can delete low flow rate alarm low FAL will be blocked. Okay, the final steps of this last step, flow rate relay, flow rate relay, signal on relativity. We have two options here. Point and measure point. and vice versa. And opening instruction for the program. Otherwise, or other things, no. To be honest, the same description can be applied on the temperature, pressure, and level. For example, if we want to go here, as in the presentation, we have TE, maybe T transmitter, TH, TAL, TST, for temperature. And here, instead of flow rate, we will go on temperature, right? The same description. Why? Because the methodology and philosophy of control are the same. Okay. Flow rate, temperature, maybe not in the naked gas, maybe, for example, the vessel, the temperature. The transmitter, so, okay, and the pressure the same for the pressure, and so on, and similar to delivery. Okay, thank you. We have finished this class, and I wish if you have any question or you need any supplementary documents from me, you can email us at the email in our website. And thank you very much for your attendance.